Hey everybody, welcome back for our 13th installment of our AP review series. And today we're going to continue to look at integral applications. Last time we looked at more particle motion focus, looking at velocity and acceleration and their connection back to position. Today we're going to focus in on other rates of change and then how to handle the word average on the AP. So let's begin like this. Let's let R of t be the rate that water is flowing into a tank. So R of t represents this rate of change that water is flowing into some tank. And I picked water flowing into a tank. This could be anything, right? This could be the rate that snow is falling on the ground. This could be the rate that, what was the 2013? Gravel was brought to a processing plant, or whatever it is, right? So the main thing we want to focus on here is the idea of the integral is net change, right? So if I were to integrate this rate of change, fundamental theorem of calculus would say that the antiderivative of rate, I'm going to call that the amount of water. So this would be equal to the change in amount from time A to time B. The difference between how much was there at time A versus how much is there at time B. So this is how much water goes in. How many gallons of water flow in? Now, a lot of times these problems involving rates of change have a second rate. So let's say G of t. Let G of t be the rate water is flowing out. Well, I won't say flowing, it's leaking, can't spell, is the rate at which water is leaking. So now you have a rate that water is leaving the tank. So this often gets tied into a problem. Let's say that the amount of water at time A is given. So the tank begins with a certain amount of water at time A. And then let's say that from time A to time B, a certain amount of water flows in. This would be, if there was only a rate in, this would be how much water there is at time B. But now our problem is introduce this rate out. And these problems on your AP exam are written so that they're positive. So rate out needs to be subtracted when you do this. This would give me the amount of water at time B, because this represents how much we begin with at the start, plus how much goes in. So this is initial, plus the amount that goes in, minus the amount that goes out, to give me the new amount. And you might see a relationship, hopefully you do, between last time when we talked about initial position plus change in position is new position. So this is initial amount plus change in amount, which is modeled by two different equations here to create new amount. So it's a really, like, all of this stuff is so connected. Don't try to separate it into different things. Focus on all of it as sort of the same understanding of the fundamental theorem of calculus in its application. So be ready for problems involving rates of change. If we continue with this, what do certain things represent? So what if I just said R of t minus G of t, rate in minus rate out? This would represent the derivative, right? How fast is the amount changing at an instant, A prime of t, which then you could use to optimize, right? If I set this equal to 0, if we said R of t minus G of t equals 0, where the two rates are the same, this would represent a critical value for the amount A of t, and would help us to do optimization problems with this. So I can determine where the rates are the same and then analyze the amount at each of the candidates and run the candidate test for optimization. So we can see old derivative concepts being included here too. And I think it's important, like I said, this line right here, that rate in minus rate out is the rate of change of the amount in that problem. Okay, hopefully this helps you review for that specific application. Be ready for this to sneak in various ways. And I didn't mention this much last time. We talked graphically with the velocity, but It often shows up in a table too, where you have to use a Riemann sum to make an approximation of the integral to interpret that way. So definitely look out for those and be prepared for each of those integral approximations, which we went over in a previous lesson also. All right, one last thing I want to touch on today is the word average. So I'm going to say what average. The word average gets tossed around the AP Calc example in a lot of different scenarios. So this really ties down into two formulas. The first is the equation for the average value. If I want to know the average value of something over an interval, I would take 1 over b minus a times the integral from a to b of whatever I'm trying to find the average of f. We can extend that, and we will in a second, to some applications. The other average would be the slope between points a and b on the curve f of x. This is the average rate of change of f of x over that interval from a to b. So how does this apply to a problem? Well, if the word average gets thrown at you, you need to know which one am I supposed to do, right? So let's look at a couple of possibilities. Let's say a problem gives you the velocity of the particle and says find the average velocity. So I give you an equation for the velocity and I want the average velocity. Well, if I'm asked for the average of what I'm given, I'm always going to use average value. Now, some of you might be saying, well, no, I thought average velocity was the change in position over the change in time. And it is. Look at these two. If you look at these two equations that we've written, these are the same thing. Watch. If I look at 1 over b minus a times the integral from a to b of velocity, applying the fundamental theorem of calculus, the antiderivative of v is position, x of t. So this would be equal to 1 over b minus a times x of b minus x of a. With a little bit of algebra, those are the same thing. So it's all about what you're given. If I'm given position and I want average velocity, yeah, I'm going to do slope. Slope brings you down a level on the derivative scale, whereas this kind of keeps you right where you're at. So if you were asked to find the average of what's given in the problem, use average value. You know, this is shown up in a lot of different ways. So if I say given A of t represents the amount of water, and I'm asked to find the average amount of water. That's average value. Great. I'm given A of t and asked for the average of A of t over the interval. If I was asked for find the average rate of change of the water, then I would do my slope, A of b minus A of a over b minus a. I think this is an important concept for you to really understand on this exam, because it gets asked all the time. So take some time to let this sort of marinate with you a little bit, just to make sure that you're prepared when you see that word show up, how to handle it. Okay, guys, that's it for today. We'll come back for part 3 in our next episode, where we look at area between curves and volumes and perimeter. All right, thanks, guys, and good luck with your studying.